A very good morning, my dear students. Welcome back to your channel of learning mathematics, continuing with matrices. So far what we have done is we've seen what a matrix is. We have seen how to add matrices, how to subtract, how to do some algebraic functions, how to multiply, most importantly. So we are slowly moving up the ladder. Today in this video, today in this session what we will be learning will be another two important points. Okay, that will be like, we are going to be learning transpose of a matrix. It's a very simple topic, transpose of the matrix, but it's very important. Okay, this is going to be very important for the upcoming exercises also. Then we will be learning two types of matrices again, symmetric and skew-symmetric matrices. And of course, we will be definitely learning some of their properties also. But as I've already told you before, we are not going to be going for the proofs of the properties. We are just going to be learning how to do all this stuff. So yeah, a very interesting topic today. Transpose of the matrix that will lead to a joint, inverse, symmetric and skew-symmetric matrices. So nasla tumpong sen sisna, okay, timsunla nung simula ato kiri, okay. Priyanshu imsanungla lanuinla imsotila achet pongan sanggita imnimungla Petigrino, Ashley, Mernbala, Ronson, Imtisinap, Tinatamsa, Deha, Odimongla, Tompang Sila, Avila, Kenikali, Chubamala, Songjumi, Imtiala. The number keeps on increasing every day, so it's good to see that. Yeah, Imti is also back again. Good morning, Imti. If you still haven't hit the like button, I'd like to DDB. The number of likes and the number of people attending should be same now. I'm just kidding. That's up to you. Yeah, it will be good. It feels good. Anyway, doesn't matter. So very good morning to each and every one of you. Let us begin then with what do we mean by transpose of a matrix and what are symmetric and skew-symmetric matrices. Very simple topics. We'll try to finish it in one video, in one session. Transpose of a matrix. As usual, as always, I'll give you the definition every time. Alamnunga, good morning. Shipongunla, good morning. I'm getting used to most of the names now. So that's why it's like, as I say, there are like, we have the family every day increasing. That means there are new members every time that we go for the live sessions. So it's good to see that not only our country's population, but class 12 trying to learn mathematics matrix population is also increasing. So let A be an m by n matrix. Okay, let A be an m by n matrix. Then the matrix obtained by interchanging. Then the matrix obtained by interchanging, listen to it now, very simple, interchanging the rows and columns. It's a very simple concept. By interchanging the rows and columns of the matrix A is called the transpose of the matrix A. How we denote it? Denoted by, it's like A dash or something like A T, power T, like A transpose, no? Which indicates A transpose. So basically the concept is just this. That means if A is our matrix Aij of the order m by n, then what will be A transpose? Simple, number of rows and number of columns will exchange. So if A is a matrix denoted by Aij of the order m by n, then A transpose will be Aj, rows to columns, columns to rows, of the order n by m. It just gets reversed. So it's a very simple concept. Okay, transpose of a matrix is nothing but where we just, exchange the rows into columns, columns to rows, interchanging the rows and columns, but that's all. Done, I guess. I'll wrap off now. I'll give you an example. Like with examples we always learn better. So like if A is one matrix like 2, root 2, 0, 1, 2, 3. Maybe something like this. So this is of the order 2 rows, 3 columns. 1, 2, 3, 3 columns. Then what will be the transpose of the given matrix? You can give it a try. Transpose of the given matrix. Rows becomes columns. 2, root 2, 0. Rows will become columns. So the order is 1, 2, 3 by 2. That means you can see the rows becomes the columns, no? And columns becomes the rows. So we just exchange the rows into columns and columns into rows. A very simple topic. So don't be confused with that. It's very simple. Keep it simple. We simply exchange the rows into columns, columns to rows. That's all. Okay. All right. Okay. Now, along with that, we need to keep some properties or some results. These are very useful in your multiple choice questions, JEE based questions also, engineering based questions also, but we are not going to be going for the proof. I'll just give you the results, the theorems. You can go through it if you're interested in the proof. I believe in the textbook also and many other books, the proof will be provided to you. The transpose of a transpose is A, and that's very logical only. Now, you go back, come back again. Where are you? You go, come back again. You're still at the starting place only, isn't it? So it's like the A transpose, its transpose again will be simply the matrix A only. I think without example also that's fine. Okay, one example I'll give you. Suppose matrix A, 1, 2, just a proof, actually not needed, but anyway, I'll just give you. What will be its transpose? Then that's going to be 1, 2, no? Rows will change to columns, 3, 1. Then what will be the transpose of the transpose? Then again, 1, 3, 2, 1. So what do we have here? We have the same matrix back again. That's what the theorem states. So the transpose of a given matrix is the matrix itself. A scalar multiple, scalar always is a scalar. Scalar is not affected by the operation of transpose and so on. I think this is done. You can have your own examples also. A plus B transpose will be A transpose plus B transpose. Same thing for my. But A into B whole transpose, not like addition or subtraction. We are not going to be having A transpose B transpose. Okay, no, because the concept is very simple. When we have A transpose A into B, then we mean we will not go for the proof. Okay, but let me just give you a small brief explanation, like if you can just use our thoughts. A into B. Now A into B will be conformable only if the number of columns is equal to the number of rows. That's how we multiply. But if you go for its transpose, then everything will be just now reverse, ulta, isn't it? So that means B transpose into A transpose. There is a proof for that, but as I say, we will not go for the proof. But remember, the concept is this. Transpose means where the rows are changed to columns, columns to rows. So definitely for addition, of course, it will not matter, but answer, of course, may be different. No, this will be verified, but for multiplication, what happens is, see, addition is very simple because they will be conformable for addition only when they are of the same order, comparable. So the order won't change, but multiplication, we know that the order really plays a part in the multiplication of matrices. So that's why A into B transpose will be B transpose into A transpose. Number of columns is equal to number of rows. That's the way we do our matrix multiplication. But yeah, just the result is needed here for now. The proof and all, yeah, basically not needed in up to class 12 standard. You will do that in your higher classes. Proof. Alright, so now the next that gives rise from transpose to the next topic are, first one, symmetric matrix. I hope you understand the meaning of symmetric. That will have, whatever topics are given, they will have almost the same meaning. Same. It means something. The topic is symmetric. Symmetric means what? What do we mean by symmetric logically? Basically, symmetric means that's perfectly symmetric. Both sides is same, cut into two equal halves. There are many the mirror image and all. So that means what happens here for symmetric matrix is, again, as usual, I will give you the definition. A square matrix A. A square matrix A is said to be symmetric if the transpose of A is same as the matrix itself. So when we have this special condition, then we say that that particular matrix is a symmetric matrix. Example, what I mean is, concept is very simple again. Like 4, 3, 3, 2. For example, if you have a matrix like this. Excuse me. Since I'm using chalk, dust allergy to chalk, as many of you know. Okay. Please pardon me. So A, if this is a matrix given to us, then what will be the transpose of A? Transpose of A, rows to columns, columns to rows, as we know it. So, rows to columns. 4, 3, you can just stick to one, okay? Either you just stick rows to columns or you stick to like columns to rows. You stick to one, don't like confuse within the same matrix, don't try to change the rows, columns, and again columns, rows, and all. You stick to one, you decide what do you want to change. That is very important. If you want to change the rows to columns, you stick on that particular matrix. If you decide to exchange columns to rows, then you stick to that in that particular matrix. Okay, don't confuse. So I'm sticking to rows to columns and rows to columns. Now what do we have here? It's the same matrix. So you can see there are certain special matrices which does exist. whose transpose you take, you get the same matrix. It doesn't really matter at all. So if you come across this kind of special matrices, then these matrices are said to be symmetric matrix. Symmetric matrices. Alright? Okay, now with that, there's another one. The next one. Skew-symmetric matrices. The matrix A square matrix, always a square matrix, not rectangular matrices. A square matrix is said to be, I'll just continue here. Skew-symmetric if the transpose of the matrix is equal to negative of the matrix. That's the condition with skew-symmetric matrices. If the transpose of the matrix is equal to the negative of the given matrix. Alright, example will be something like 0, 5. There's one unique property with this skew matrix. I'll give you that also. What will be its A transpose? Rows to columns. 0, 5, minus 5, 0. Remember, we are not trying to deal with a symmetric matrix, so don't expect to get the exact same matrix. We expect to get negative of A. That means minus, if we can just take common, minus 1. Then 0, it becomes plus 5, minus 5, 0. And this is the matrix A. So now here we can see that A transpose will provide us the result minus of A. So this kind of matrices will be known as skew-symmetric matrices. Alright, so if the transpose of the matrix is same to itself, then it's a symmetric matrix. If it is a negative of that matrix, then it's a skew-symmetric matrix. Alright, so that's simple. Now there is a unique property with skew matrix. I'll give you that. One unique property about this skew matrix is, we will not go for the proof again, every diagonal element of a skew-symmetric matrix is 0. This is one special property about a skew-symmetric matrix. Every diagonal element of a skew-symmetric matrix is always 0. So that's why, if you remember, the matrix that I gave you before was 0, 5, minus 5, 0. So you could see that the diagonal elements A11, A12 were 0. So you'll find that in every skew-symmetric matrix that the diagonal elements will be 0. That's one way to recognize a skew-symmetric matrix. Okay, its diagonal elements will always be 0. If so, I do not know what example, like, I mean, even if you just take a rough example like 0, 2, 1, 0, 0, 1, 2, 1, 0, something like this. So this may be a skew-symmetric or a symmetric matrix, but what I'm trying to tell you is, like, every diagonal element will always be 0. Every diagonal element of a skew-symmetric matrix will be 0. Of course, we do not know whether this is symmetric or skew-symmetric, but that's one property. That means if the diagonal elements are not 0, one thing is for sure, that is, that matrix is definitely not skew-symmetric. It is definitely not skew-symmetric. Alright? Okay. Now, time for some results again. Again, we are not going to go for the proof, we just need the results. like some results. I'll just straight away give you the results only, okay? Of course, first result is, like, you can go to the textbook, so we are not going to waste time on those results. Like, the sum of two symmetric matrix is always a symmetric matrix. The sum of two skew-symmetric matrix is always a skew-symmetric matrix. Some properties, no? I think that you will understand. I'll just give you some important properties only. That is this one, first one. For any square matrix, remember, these are the properties I'm giving you are not exhaustive, okay? Like, it's not complete. Like, there are other properties also. I'm just giving you some of the important properties. You can go to the textbook, you'll find many more other properties also. Like, as I just said, the sum of two symmetric matrix is a symmetric matrix. The sum of two skew-symmetric matrix is also a skew-symmetric matrix. Likewise, simple properties. But these are some basic important properties. Like, for any square matrix A with real number entries. Real number entries means like with real numbers, not imaginary numbers or complex numbers and so on. The first one is so for any square matrix, what happens? The matrix formed by adding the matrix to its transpose, A plus A transpose, is always symmetric. The second one will be the matrix subtracted. That if you subtract the transpose of the matrix with the original matrix, you will get a skew-symmetric matrix. So if for any square matrix A plus A transpose is also always symmetric, A minus A transpose is skew-symmetric. So just in case, like, they give you a matrix A, just in case like they give you a matrix A and then they tell you find out maybe a skew-symmetric matrix. So all you have to do is find out its transpose and subtract it from the matrix. You will have your skew-symmetric matrix. So the symmetric matrices, skew-symmetric matrices are not very difficult to find out, or not very difficult to evaluate, or not very difficult to discover. Okay, we can get that from any of the matrix given to us. Just subtract it to the transpose, you will have your skew-symmetric matrix. Add it to the transpose, you will have your symmetric matrix. Okay, this is the first property. So basically, like, these are used in multiple choice questions. This one is important. The other properties are next properties that I'm going to give you now. Problems based on this we have. Every square matrix. Every square matrix is expressible. Every square matrix is expressible as the sum of a symmetric and skew-symmetric matrix. This is important. What it says, every square matrix can be expressed any square matrix. can be expressed as the sum of a symmetric and a skew-symmetric matrix. What it means is, if you have a square matrix A, remember this note, square, it should be only square matrices, okay? If you have a square matrix A, then that square matrix can be expressed or like expanded or expressed as the sum of a symmetric and a skew-symmetric matrix, something like this. That means A can be expressed as the sum of two matrices, symmetric, one skew-symmetric. The concept is simply this: we know that A plus A transpose is always symmetric for any given matrix A, and A minus A transpose is also always skew-symmetric for any given matrix A. But what are we trying to do here? We're trying to express A. So A transpose minus A transpose, I'm just trying to give you a small verification proof. A transpose, we can cancel. A plus A will have 2A, it has to be A, so just balancing the equation, half of half. So this is how a matrix can be expressed, that is generally written as P plus Q, where P represents this matrix, which is going to be a symmetric matrix, and Q will represent this matrix, which is supposed to be a skew-symmetric matrix. That means a square matrix A can be expressed as a sum of a symmetric and skew-symmetric matrix. Mathematically, how do we denote that? That is, A can be written as P plus Q, where P is half of A plus A transpose, Q equal to half of A minus A transpose. A plus A transpose, we know that these are symmetric matrices. A minus A transpose, just now only we have seen in the theorem, it is always skew-symmetric. Half comes because, just to balance the equation, because A has to be expressed as this. So like A transpose cancel, half of A plus half of A. Mathematically also it has to be correct, isn't it? We just cannot give one statement, whereas mathematically it's not balanced and then it doesn't prove to be correct. So mathematically also it has to be correct. So that's why this half comes. Alright, so that's how you will be proving if you have to prove, which is not needed, of course. Alright, so this is important. So yeah, in this exercise we have these few new topics, that is the transpose, the symmetric, and the skew-symmetric matrix. So that's all that we have here. We will move to the exercise. We'll try to solve some questions from the exercise today. So let's move on to the exercise, that is exercise 3.3. Exercise 3.3. First question, find the transpose. Find the transpose of each of the following matrices. Number 1. 5, 1 by 2, minus 1. So for the first one, I'm just writing let A equal to this one directly, okay? Let A equal to this matrix. So what will be its transpose? Rows to columns, columns to rows. So it's simply going to be, so here we had one row. So we'll have here 3 rows. So this was of the order 3 by 1. So this will become of the order 1 by 3. Just change the rows to columns, numbers. 1 row, 3 columns, 3 rows, 1 column. Similarly, I'll just do the third one. Alright, so the first question was an easy one. Let's move on to the second. Second question is, if the matrix A is given as -1, 2, 3, 5, 7, 9, -2, 1, 1. And the matrix B given as -4, 1, -5, -4, 1, -5, 1, 2, 0, 1, 3, 1. 1, 2, 0, 1, 3, 1. So the matrix A and B are given like this. Then what are we supposed to do is verify. Number one, verify that that proof that result which I gave you. So that's why A plus B transpose is equal to nothing but A transpose plus B transpose. So let's do that quickly. A plus B. We'll just do it directly now. Let's try to add the matrix directly from the question. That is A plus B. Let's not write down all the steps and all. So A plus B -1. Do I have to write down? Do I have to write down, or it's all right? Okay. All right. So also if we add -1, -4, -5, 2 plus 1, 3, 3 minus 5, -2, 5 plus 1, 6, 7 plus 2, 9, 9 plus 0, 9, -2 plus 1, -1, 1 plus 3, 4, 1 plus 1, 2. So that's our matrix A plus B. -5, 3, -2, 6, 9, 9, -1, 4, 2. That's fine. So I'll be keeping this matrix, okay, because in the next question also I will be needing this, so I'll be just keeping this matrix for now. That's for me, for myself. Alright, so A plus B is that. So what is A plus B transpose? A plus B transpose will be -5, 6, -1, 3, 9, 4, -2, 9, 2. So this is our A plus B transpose. Now let's find out A transpose plus B transpose. I'm going to do it directly here. A transpose, I'll just directly convert, okay? -1, 5, -2, 2, 7, 1, 3, 9, 1. Plus B transpose. B transpose -4, 1, 1, 1, 2, 3, -5, 0, 1. So A transpose plus B transpose. What do we have? If we add, then it's like -1, -4, -5, 5 plus 1, that's 6, -2 plus 1, -1, 2 plus 1, that's 3, 7 plus 2, that's 9, 1 plus 3, that is 4, 3 minus 5, that's -2, 9 plus 0, 9, 1 plus 1, that's 2. Now you see, compare, -5, 6, -1, 3, 9, 4, -2, 9, 2. That's fine, so that's why, yeah, that's our result. So I think this is not needed anymore. So that is equal to A plus B transpose, hence verified. keep this also. The second verification is A minus B transpose will be A transpose minus B transpose. Second question. So I'm going to find out A minus B first. Or I can directly do here. No. Let's not confuse too many steps. A minus B. So A minus B. Minus 1, 2, 3, minus 1, 2, 3, 5, 7, 9, 5, 7, 9, minus 2, 1, 1, minus 2, 1, 1, minus B. Minus 4, 1, minus 5, 1, 2, 0, 1, 2, 0, 1, 3, 1. So if we subtract, what do we have? Minus 1, minus 4, again minus 5. 2 minus 1, that's 1. 3 minus 5. So 3, that's 3 plus 5. So that's going to be 8. Right? 5 minus 1, 4. 7 minus 2, 5. 9 minus 0, 9. Minus 2, minus 1, minus 3. 1 minus 3. Minus 2. 1 minus 1, 0. So that's A minus B. So A minus B, 3. Sorry, minus 1, minus plus 4. So minus 1 plus 4, that's going to be 3. So we have 3, 1, 8, 4, 5, 9, minus 3, minus 2, 0. So then what will be the transpose? A minus B transpose? A minus B transpose will be now 3, 4, minus 3, 1, 5, minus 2, 8, 9, 8, 9, 0. Alright, now let's find out A transpose minus B transpose. So this is already transposed, so directly just subtraction only. Minus 1, okay, I'm going to be extra careful here now. Minus 1, minus plus 4, that's 3. 5 minus 1, 4, minus 2, minus 1, minus 3. 2 minus 1, 7 minus 2, 1 minus 3, 3 minus plus 5, 8, 9 minus 0, 1 minus 1, 0. Let's check. 3 minus 4, 3, 1, 5 minus 2, 8, 9, 0. So this is of course equal to A minus B transpose. Yeah, Hilon, I got it. That's why I corrected there. Minus 1, minus plus 4, 3. You'll have to bear that with me because we do it on the board. So, as I always say, no, these small things happen. Thank you for correction. Thank you for correction. Actually, I really appreciate that. Thank you for your correction because I really do appreciate that. Okay, because it means that you are listening and then you are doing. So that's really very encouraging for me because it proves that you're just not sitting and watching on the bed and all. That means you're doing it. You're doing it along with us. So that's really appreciative. I really appreciate that. Okay, thank you so much. That means we are really learning. Alright, so that's question number 2. And question number 3 also will be similar. Okay, 3 also is almost the same. Of course, just the order of the matrix is slightly different. So that of course I guess you can do. We'll do one more question. Number 4. If A transpose is minus 2, 3, 1, 2. Note, take a note here, not A. A transpose is given. So you have to be careful, sometimes these small things slip out of our vision. Then we're supposed to find out A plus 2B whole transpose. Transpose of the matrix A plus 2B. So to find out A plus 2B, it's quite simple, but what do we need? We will need the matrix A. And that's why we had that, you remember the result that I gave you just a few moments ago? How do we find out the matrix A? We know that the matrix A is the transpose of the transpose of the given matrix. So let's find out the transpose of this matrix, that is minus 2, 3, 1, 2. Its transpose, because this is a transpose, its transpose, that's going to be minus 2, 1, 3, 2. This is our matrix A. There we have it, our matrix A, minus 2, 1, 3, 2. And the matrix 2B for the result will be, I'm going to do it directly, okay, minus 2, 0, 2, 4. All of you are quite capable of understanding these simple things, so I'm just doing it directly there. Alright, so that's it. Let's go for the result quickly. So what we need is, first, we need the matrix A plus 2B. After that, we will go for its transpose. Take it one step at a time, okay? Do not try to you just sum up all the steps in one go. So this matrix will be minus 2 plus minus 2, 4, 1 plus 0, 3 plus 2, 2 plus 4. So the transpose of the matrix A plus 2B will be nothing but minus 4 by 1, 6. Minus 4, 5, 1, 6. Alright, so just be extra careful when you look at the questions. Always do go through the questions properly. Small things, they slip out of our mind. Okay, I'll focus. Alright, so I guess that should be enough for me. In the next session, we will try to solve the remaining part of the exercise. We'll try to finish, and after that we'll have the other exercise that's about elementary row operations, invertible matrix. So we are almost nearing the end of the matrix chapter without even knowing it. Okay, so that means we're all enjoying it. So alright then, I'll see you in the next session again, next class. So thank you so much all for being so attentive, so for being especially so decent. I really appreciate that. Thank you all, thank you so much. I'll see you again. Alright, so have a good day all of you, and yes, do stay safe. Thank you all for joining. Definitely, thanks a lot. It means a lot to me, okay?